April 6, 1945, East China Sea, off Okinawa. Dawn breaks over Task Force 58 of the United States Fifth Fleet. On radar picket destroyers stationed 16 miles from the main force, sailors scan the horizon. They already know what is coming. Inside the Combat Information Center aboard USS Lee, radar operators track incoming contacts. Not dozens, hundreds. Gun crews on deck load 5-inch shells marked with the mysterious letters VT, proximity-fused ammunition containing tiny radio transmitters that will change naval warfare forever. The objective is brutally simple: survive. This is Operation Kikusui No. 1, the first of 10 massive coordinated kamikaze assaults. At 0600 hours, the sky begins to fill. Through the morning haze comes a sound that will define the Battle of Okinawa, the deep growing drone of hundreds of aircraft engines advancing in waves. These pilots are sealed inside their cockpits with no intention of returning. Leading the attack are the Imperial Japanese Navy's Special Attack Units. Zero fighters and Yokosuka D-4Y dive bombers, each carrying 250-kilogram bombs, spearhead the assault. Behind them follow waves of older aircraft pressed into suicide service. Among them are the most feared weapons of all: Oka pilots, sealed inside rocket-powered flying bombs carried beneath Mitsubishi G4M bombers. What follows will demonstrate the revolutionary power of American proximity fuse technology and reveal why kamikaze tactics, devastating at first, would ultimately fail against the most advanced anti-aircraft defense system ever deployed. The VT proximity fuse had only recently arrived in the Pacific after 2 years of intense combat testing that began with a single historic shot. Developed under a crash program launched in 1940 by Section T of the Johns Hopkins Applied Physics Laboratory, led by Dr. Merle Tuve, the proximity fuse became one of the 3 most critical secret projects of World War II, alongside radar and the atomic bomb. Its principle was elegantly simple. Each shell carried a miniature radio transmitter and receiver that emitted continuous radio waves. When those waves reflected off an aircraft and returned with a Doppler shift indicating close proximity, the fuse detonated automatically. Gunners no longer needed precise range estimates or mechanical timers. The shell decided when to explode. The engineering challenges were immense. Tiny glass vacuum tubes, many manufactured by Sylvania, had to survive launch forces exceeding 20,000 times gravity. Fired from a 5-inch gun, the projectile traveled at 2,600 feet per second, spinning at 25,000 revolutions per minute. After that violent launch, the fuse still had to function flawlessly in temperatures ranging from 100 to -50 degrees Fahrenheit. By April 1945, American industry had produced over 15 million proximity fuses for naval use in the Pacific. Production was spread across dozens of contractors. Crossley Corporation alone manufactured nearly 5.2 million fuses, nearly a quarter of the total. RCA, Eastman Kodak, General Electric, McQuay Norris, and 87 other firms operated across 110 factories in a massive industrial effort. As a result, U.S. forces at Okinawa were equipped with the most advanced anti-aircraft ammunition ever created. The Navy increased proximity fuse usage from 25% of anti-aircraft rounds in 1943 to 75% by 1945, acknowledging that kamikaze warfare required a revolutionary defense. Every destroyer, cruiser, and battleship carried thousands of VT-fused shells as its primary shield. The Japanese kamikaze program, by contrast, was born of desperation.
After catastrophic losses in the Marianas and the Battle of the Philippine Sea, Japan had lost most of its experienced pilots and carrier strength. In October 1944, Vice Admiral Takejiro Onishi proposed the creation of special attack units, arguing that conventional tactics could no longer succeed against overwhelming American firepower. Kamikaze attacks transformed inexperienced pilots into human-guided weapons. On paper, the mathematics seemed favorable. Conventional air attacks achieved hit rates of barely 2% against well-defended U.S. ships. Early kamikaze attacks in the Philippines exceeded 34% success. A single Zero fighter carrying 250-kilogram bombs could cripple or sink a destroyer, trading one pilot and one obsolete aircraft for hundreds of American casualties and millions of dollars in damage. Training was brief and focused more on spiritual readiness than flying skill. Many pilots had fewer than 100 flying hours, compared to over 500 hours for Japan's elite aviators earlier in the war. Instruction emphasized navigation, ship recognition, and the final dive meant to evade anti-aircraft fire. Pilots wrote farewell letters, shared ceremonial sake, and were given samurai swords or rising sun headbands before departing. But no amount of ritual could overcome the technological storm waiting ahead. The Oka represented the ultimate expression of the kamikaze idea. Known to American sailors as Baka, the Fool, it carried a 1,200-kilogram warhead powered by 3 solid-fuel rockets. In its terminal dive, it could reach 575 miles per hour, seemingly unstoppable. Yet it carried a fatal flaw, a range of barely 10 miles, forcing vulnerable Betty bombers to approach dangerously close to American defenses. At Okinawa, American ships formed concentric rings of protection. Radar picket destroyers stood far forward, providing early warning and absorbing the first blows. Each destroyer mounted 12 to 16 5-inch guns, all firing VT-fused shells that created overlapping walls of explosive fire. The VT proximity fuse transformed anti-aircraft guns from area denial weapons into precision killers. A VT-fused shell had a lethal radius of 70 feet compared to just 20 feet for traditional time-fused rounds. Even more important, it eliminated complex calculations, allowing gunners to fire immediately upon detection. On April 6, 1945, these systems faced their ultimate test. Operation Kikusui No. 1 launched 524 aircraft, 391 Navy, and 133 Army planes. Of those, 297 were kamikazes. The largest suicide air assault in history was about to collide with the most sophisticated naval defense system ever created.
A total of 297 suicide aircraft were committed in a single coordinated assault. Commander Frederick Julian Beckton of USS Laffey later described the approaching kamikaze formations as a swarm of bees converging on the only flower in the desert. The first wave struck at 0600 hours, with radar operators tracking more than 50 aircraft advancing from the north. Radar picket destroyers opened fire at their maximum effective range, 12,000 yards, launching VT-fused shells into the incoming formations. The results were immediate and devastating. Each shell that passed within lethal distance of an aircraft detonated automatically, filling the sky with razor-sharp steel fragments. Unlike time-fused rounds, which demanded precise range calculations, the proximity fuse transformed near misses into kills. Within minutes, dozens of Japanese aircraft plunged into the sea. Their suicide missions ended far from their targets, but the waves continued to press forward.
At 07:44 hours, USS Laffey came under an intense, concentrated assault. Over the next 80 minutes, 22 aircraft attacked the destroyer. Her gunners fired 345 rounds of 5-inch VT ammunition, destroying 9 attackers outright. The proximity fuse allowed Laffey's guns to shift instantly between targets, engaging multiple aircraft without the delays imposed by mechanical fuse setting. When Kamikaze pilots attempted their standard tactic, approaching at wave-top height to evade radar, the VT fuse proved just as lethal. Shells detonated when passing close to the sea's surface, creating walls of fragments that tore through low-flying aircraft. Despite the ferocity of the defensive fire, Laffey was struck by 6 kamikazes and 4 bombs, yet she survived, a testament to American damage control and to the fact that proximity fuses had stopped many more attackers from ever reaching her hull. The effectiveness of the VT fuse was no accident. The technology had been secretly tested in combat since January 5, 1943, when USS Helena fired the first proximity-fused shells in action off Guadalcanal. Lieutenant Red Cochran, commanding the aft 5-inch battery, shot down a Japanese Aichi D-3A Val dive bomber with the second of 3 salvos. The shells never struck the aircraft directly, they simply passed close enough to trigger detonation and shred it with fragments. That single success validated 3 years of intensive development that had overcome enormous technical challenges. Each fuse contained approximately 130 electronic components, miniaturized to fit inside a space smaller than a pint milk bottle, all manufactured to tolerances measured in thousandths of an inch. By the Okinawa campaign, post-battle analysis revealed the stark mathematical advantage of proximity-fused ammunition. Time-fused 5-inch shells required an average of 1,162 rounds to destroy a single kamikaze. VT-fused shells reduced that figure to 310 rounds per kill, nearly a 4-fold increase in efficiency. In ideal conditions, the results were even dramatic. In May 1945, the destroyer escort USS Abercrombie destroyed a kamikaze with just 2 VT rounds. On May 4th, USS Morrison shot down 8 attackers in minutes using proximity-fused ammunition before ultimately being overwhelmed by sheer numbers. The psychological impact on Japanese pilots was profound. Kamikaze aviators who aborted their missions described the terror of approaching American task forces through what felt like solid walls of exploding shells. The distinctive black bursts of VT detonations appeared with uncanny precision, as if American gunners could see the future path of every aircraft. Japanese doctrine assumed that high-speed, low-altitude approaches would minimize exposure to anti-aircraft fire. The VT fuse shattered that assumption completely. Shells that would have missed by 50 feet using conventional fuses now detonated lethally close, turning the final attack run into a corridor of precisely timed explosions. Vice Admiral Matome Ugaki, directing kamikaze operations from Kyushu, noted the growing effectiveness of American defenses in his diary. By late April 1945, Japanese naval intelligence estimated that fewer than 1 in 4 kamikaze aircraft were reaching their targets, down from 1 in 3 during the Philippines campaign. The decline was attributed primarily to what Japanese reports described as a new type of anti-aircraft shell that explodes with impossible accuracy. Ugaki wrote, "The enemy's defensive firepower has increased remarkably. Our special attack aircraft are being destroyed at distances we previously considered safe." Individual American sailors operating 5-inch guns with VT ammunition became legends within their task forces. Aboard USS Hugh W. Hadley, gun crews claimed 17 confirmed kamikaze kills during the May 11th attack. They developed a technique of continuous lead fire, creating a moving wall of VT detonations that attacking aircraft were forced to fly through. Firing up to 15 rounds per minute, each shell carried its own electronic brain, seeking targets independently. During a 52-minute period, USS Hugh W. Hadley destroyed multiple kamikazes in rapid succession. Even shells passing above or below violently maneuvering aircraft detonated with lethal effectiveness. The experience of USS Aaron Ward during the May 3rd attacks further demonstrated the proximity fuse as a force multiplier. When 40 kamikaze aircraft attacked the destroyer, her 5-inch batteries fired continuously for 52 minutes. VT-fused shells destroyed 6 attackers outright and damaged 5 more so severely that they crashed into the sea. Commander William Saunders later stated that without proximity fuses, his ship would have been overwhelmed within the first 10 minutes. Across the fleet, similar stories multiplied. During the 10 major Kikusui operations from April 6 to June 22, 1945, Japanese forces launched approximately 1,900 aircraft in organized kamikaze attacks. American naval forces, relying primarily on VT-fused 5-inch ammunition, destroyed hundreds before they could reach their targets. Operations research statistics revealed the final truth. Ships equipped with proximity-fused ammunition were 3 times more likely to survive concentrated kamikaze attacks than those relying mainly on conventional anti-aircraft shells.
The proximity fuse transformed what should have been a catastrophic tactical breakthrough into a costly but controllable threat. As the Okinawa campaign progressed, the gap in technological adaptation became increasingly apparent. American forces continuously refined their use of VT-fused ammunition. Gunnery officers discovered that proximity shells were most lethal when fired in coordinated patterns that created overlapping spheres of fragmentation. Ships began synchronizing their fire to form what sailors called VT boxes, corridors of exploding steel through which kamikaze aircraft were forced to fly. The Japanese response could only be tactical improvisation. Dawn attacks, multi-axis approaches, mixing conventional aircraft with suicide planes, none could overcome the fundamental advantage of shells that knew precisely when to explode. Industrial production figures told the larger story of modern warfare at its peak. By June 1945, American factories were producing 70,000 proximity fuses per day. Over the course of the war, more than 22 million VT fuses were manufactured at a cost exceeding $1 billion in 1940s currency, roughly $15 billion today. Crosley Corporation alone employed 10,000 workers, operating 3 shifts, 7 days a week. Through mass production efficiencies, the cost of a single fuse fell from $732 in 1942 to just $18 by 1945. This investment paid off. Navy analysis later concluded that proximity fuses prevented the loss of dozens of ships during the Okinawa campaign alone. Japan could produce nothing comparable. Although Japanese scientists understood the theoretical concept of the proximity fuse, and German reports describing Allied special ammunition had reached Japan by submarine, the nation lacked the industrial base to develop or mass-produce such devices. Precision vacuum tube manufacturing was far beyond the capacity of Japan's bomb-damaged, resource-starved industry. Japanese radar development, essential to understanding proximity fuse principles, lagged far behind American systems.
The Type 22 radar, Japan's most advanced naval set, operated at wavelengths that made miniaturization impossible, even if manufacturing capacity had existed. As losses mounted, the effectiveness of the proximity fuse forced changes in Japanese tactics. By May 1945, kamikaze pilots were instructed to approach American task forces at maximum altitude, then dive vertically onto their targets in an attempt to reduce exposure to VT-fused fire. While this reduced losses during approach, it made accurate targeting nearly impossible. American ships could maneuver out of the dive path, and the high-altitude approach gave radar operators more time to track and vector defenses. The adjustment proved counterproductive. Admiral Richmond Kelly Turner, commander of amphibious forces at Okinawa, later credited proximity fuses with making the invasion feasible. In a letter to the Chief of Naval Operations, Turner wrote, "Without the VT fuse, our losses from suicide attacks would have been unbearable. The Japanese kamikaze was a formidable weapon that could have changed the outcome of the Pacific War if not for our technological superiority in anti-aircraft defense." His assessment was echoed by Admiral Mark Mitcher, whose flagship USS Bunker Hill survived a devastating kamikaze strike on May 11th, in part because proximity-fused fire destroyed 3 additional attackers that would likely have finished the crippled carrier. Admiral Arleigh Burke, Mitcher's chief of staff, recalled the impact years later. "When I went as Chief of Staff to Admiral Mitcher, all the 5-inch by 38 and 5-inch by 25 ammunition was fitted with VT fuses. Those fuses knocked down enemy planes by the dozens. Had it not been for them, our ship losses and casualties in the fast carriers during the last half of the war would have been enormously greater." The impact of the proximity fuse went beyond statistics. It undermined the psychological foundation of kamikaze warfare itself. Japanese doctrine assumed that the certainty of pilot death would be balanced by near certainty of hitting the target. Once success rates fell below 20%, the exchange became unsustainable, even by the brutal logic of suicide warfare. Many kamikaze pilots, often university students hastily drafted into special attack units, began to realize that their deaths would likely achieve nothing. Letters recovered after the war revealed a growing awareness that American defenses had evolved far beyond what their commanders had promised. Lieutenant Yutio Seki, leader of the first official kamikaze unit in October 1944, had achieved devastating success in Leyte Gulf when proximity fuses made up only 25% of American anti-aircraft ammunition. By Okinawa, his successors faced an entirely different battlefield. On March 21, 1945, Lieutenant Commander Goro Nonaka, leading the Thunder God Corps equipped with Oka flying bombs, lost his entire unit without a single weapon reaching launch range. All 18 Betty bombers were intercepted and destroyed by American fighters, guided by radar intercept officers. Even if they had broken through, the wall of VT-fused anti-aircraft fire awaiting them would have been impenetrable. The proximity fuse represented more than superior manufacturing. It embodied a convergence of electronics, materials science, and systems integration that Japan could not match. Miniaturized vacuum tubes produced by Sylvania and Raytheon used special glass capable of surviving enormous shock forces. The battery system, inert during storage, activated instantly under the acceleration of firing. The radio frequency was carefully selected to minimize interference while maximizing detection accuracy. Each component reflected years of focused research backed by virtually unlimited resources. Japanese anti-aircraft defenses remained comparatively primitive. The Type 98 100mm gun, Japan's most capable heavy AA weapon, relied on manually set mechanical time fuses. Even the super battleship Yamato, during her final sortie, carried anti-aircraft ammunition little more advanced than what Americans had faced at Pearl Harbor. On April 7, 1945, Yamato confronted more than 300 American aircraft. Her 162 anti-aircraft guns fired thousands of rounds, yet shot down fewer than 10 attackers. The Americans lost just 10 aircraft while sinking the largest battleship ever built. The disparity was undisputable. The proximity fuse also enabled entirely new defensive concepts impossible with conventional ammunition. American destroyers developed the VT umbrella technique, firing proximity-fused shells in pre-planned patterns above friendly ships under attack, creating a protective canopy of detonations that no diving aircraft could penetrate. The shells detonated at carefully calculated distances, forming a protective dome of fragmentation that kamikaze aircraft were forced to penetrate. This technique proved especially effective against the Oka flying bombs. Their extreme speed made them difficult targets for conventional fire control systems, but they remained fatally vulnerable to the invisible wall of steel fragments created by coordinated VT firing patterns. During the Okinawa campaign, from April 1 to June 22, 1945, the United States Navy expended approximately 150,000 proximity-fused 5-inch shells. The results were decisive. Although VT-fused ammunition accounted for roughly 45% of heavy anti-aircraft rounds fired, it was responsible for the majority of confirmed kamikaze kills at long range. Time-fused shells, which made up the remaining 55%, proved effective mainly at close range where accuracy was less critical. The mathematics were unequivocal. Proximity fuses were 3 to 4 times more effective than conventional ammunition against kamikaze attacks. The difference in human cost was equally stark. Ships that exhausted their VT ammunition and were forced to revert to time-fused shells experienced dramatically higher casualty rates in subsequent attacks. On May 28, the destroyer USS Drexler, after expending her supply of proximity-fused ammunition, was struck by 2 kamikazes and sunk in less than 1 minute. Her 58 dead exceeded the total casualties suffered by many destroyers over entire campaigns. Both attackers would likely have been destroyed had VT fire still been available. Even senior commanders experienced the kamikaze threat firsthand. Admiral Raymond Spruance, commander of the Fifth Fleet, saw his flagship USS Indianapolis struck by a suicide plane in March 1945, forcing him to transfer to USS New Mexico, which was also hit in May. He later wrote, "This is my second experience with a suicide plane making a hit on board my own ship, and I have seen 4 other ships hit near me. The suicide plane is a very effective weapon, which we must not underestimate." Yet Spruance also understood the larger truth. Without proximity fuses, the kamikaze threat would have been vastly more destructive. The VT fuse, he concluded, is the margin between bearable and unbearable losses. The strategic implications were unmistakable to planners preparing Operation Downfall, the proposed invasion of Japan. Intelligence estimates suggested that Japan had reserved nearly 10,000 aircraft for mass kamikaze attacks against the invasion fleet. American planners, confident in proximity fuse effectiveness, calculated that these attacks could be countered. VT fuse production was scheduled to reach 100,000 units per day by September 1945. New Mark 53 and Mark 58 fuses, offering improved sensitivity and reliability, were already entering mass production. The invasion fleet would have carried over 1 million proximity-fused shells, forming the most formidable anti-aircraft defense ever assembled. The atomic bombings of Hiroshima and Nagasaki ended the war before this ultimate test occurred. Yet the role of the proximity fuse in shaping Japanese surrender calculations should not be underestimated. Post-war Japanese military assessments acknowledged that defending against an invasion fleet protected by what they called electronic shells would have been impossible. Admiral Soemu Toyota, chief of the Naval General Staff, later testified that Japanese planners estimated homeland defense kamikaze attacks would achieve less than a 10% success rate against proximity-fused defenses, a level that rendered the tactic militarily meaningless. Post-war analysis revealed the full scope of the proximity fuse achievement. The program mobilized 112 companies beyond the primary contractors, creating an industrial ecosystem dedicated to producing the most advanced military electronics of the era. British scientists, who had conceived the proximity fuse concept in 1940 but lacked the resources to pursue it, later admitted that American engineers had accomplished what they believed impossible. British assessments had concluded that making vacuum tubes survive the shock of gun launch could not be done. The Americans proved otherwise. The influence of the proximity fuse extended beyond Okinawa. It marked the birth of smart munitions, weapons capable of independent decision-making. Modern air defense missiles still use proximity fusing derived directly from the VT design. The Phalanx close-in weapon system that guards today's warships operates on principles pioneered during the defense against kamikaze attacks. Electronic intelligence had defeated human guidance. Japanese veterans expressed lasting astonishment at the technology. Commander Tadashi Nakajima, one of the architects of the kamikaze program, later admitted, "We knew the Americans had superior technology, but the proximity fuse was beyond our imagination. Our pilots reported shells exploding exactly where they flew, as if guided by invisible hands." Captain Aichiro Gio, an early advocate of kamikaze tactics who survived the war, reflected, "We believed the willingness to die guaranteed success. The American electronic fuse proved that technology could defeat even the most determined human sacrifice." The contrast between kamikaze attacks and proximity fuses represented two fundamentally different philosophies of warfare. One relied on the expendability of human life. The other invested enormous resources to preserve life through technological superiority. By making kamikaze attacks survivable for American forces, the proximity fuse shattered the logic that drove thousands of young Japanese pilots to deliberate death. In this sense, the VT fuse was more than a weapon. It was a statement about the future of war. Its legacy extended into peacetime. The crash program that created the proximity fuse established a model for American scientific achievement, from the space program to modern computing. The collaboration between universities, industry, and the military that produced 22 million sophisticated electronic devices under wartime pressure defined the post-war technological order. The Johns Hopkins Applied Physics Laboratory, where the proximity fuse was perfected, went on to develop guided missiles, satellite navigation systems, and advanced defense technologies. Dr. Merle Tuve, who led the program, later reflected, "We saved lives by making weapons more effective. Every kamikaze shot down by a proximity fuse meant American sailors who went home to their families. That was worth any effort or expense." For Japan, the failure of kamikaze tactics against proximity-fused defenses marked the collapse of beliefs that spiritual resolve could overcome material reality. The pilots lost in futile attacks against walls of VT detonations became symbols not of noble sacrifice, but of leadership that failed to grasp technological truth. The cold arithmetic told the final story. 310 rounds per kill with proximity fuses versus 1,162 with time-fused shells. Those numbers translated into saved ships, preserved lives, and strategic victory. Every functioning VT fuse meant an American sailor who lived. And in the skies over Okinawa, electronics, not human sacrifice, decided the outcome of history.
A ship that survived to fight another day stood as proof that technology could provide decisive advantage in modern warfare. The confirmed destruction of hundreds of kamikaze aircraft by proximity-fused shells before they reached their targets represented thousands of American casualties prevented, dozens of ships saved, and the full validation of $1 billion investment in electronic warfare. The story of technology defeating fatalism reached its climax in the waters off Okinawa. There, radar-guided fighters, proximity-fused anti-aircraft fire, and sophisticated damage control systems prevailed against deliberate suicide attacks. The kamikaze pilots, brave young men sacrificed to a lost cause, flew into an electronic killing field their commanders had never anticipated. Their attacks inflicted horrifying tactical damage, yet they failed to achieve the strategic objective of making invasion costs unbearable. The proximity fuse had transformed kamikaze warfare from a potentially war-altering weapon into a manageable threat. Secretary of the Navy James Forrestal summarized its importance with remarkable clarity. The proximity fuse has helped blaze the trail to Japan. Without the protection this ingenious device has given the surface ships of the fleet, our westward push could not have been so swift, and the cost in men and ships would have been immeasurably greater. This judgment, echoed across the Pacific theater, reflected a central truth: electronic intelligence had defeated human sacrifice. The final accounting was grim, yet decisive. During the Okinawa campaign, kamikaze attacks sank 36 American ships and damaged 368 others. Severe as these losses were, they represented the survival of the vast majority of ships attacked, a survival rate impossible without proximity fuses. The 4,900 American sailors killed by kamikaze strikes, though marking the Navy's bloodiest battle, were a fraction of the casualties predicted without VT technology. Japanese losses were absolute. Approximately 1,900 aircraft and pilots were expended in organized kamikaze attacks during the 10 Kikusui operations, with hundreds more lost in improvised suicide missions, achieving tactical effects that fell far short of strategic necessity. The victory of proximity-fused defenses over kamikaze attacks demonstrated a fundamental principle of modern warfare. Technological superiority can overcome numbers, determination, and even the willingness to die. American sailors manning 5-inch guns armed with VT ammunition held an insurmountable advantage over Japanese pilots sealed into one-way missions. Each miniature radio transmitter in the nose of a shell represented industrial capacity, scientific mastery, and organizational power, forces no amount of martial spirit could match. When electronic intelligence met human guidance in the skies over Okinawa, the outcome had already been decided. By factories in Cincinnati, laboratories in Maryland, and a national belief that technology could preserve life while achieving victory. The mathematics were inescapable.
A proximity fuse weighing less than 5 pounds, containing 130 electronic components, manufactured for $18 by 1945 and functioning for less than 30 seconds, could destroy a kamikaze aircraft, eliminating years of pilot training, tons of material, and, most tragically, a human life that could never be replaced. Multiplied across thousands of engagements, this equation translated to strategic victory through technological superiority. The success of the proximity fuse against kamikaze attacks validated the entire American approach to 20th century warfare. Investment in science, faith in mass production, and systematic problem-solving proved decisive under the extreme conditions imaginable. For Japan, the failure of kamikaze tactics against proximity-fused defenses represented more than military defeat. It marked the collapse of a belief that spirit alone could triumph over matter. Electronic fuse defeated the divine wind, proving that in modern war, advanced technology would prevail over human sacrifice. The Pacific War demonstrated a harsh truth. In modern naval warfare, the ability to destroy aircraft at distance determines survival. Nations capable of designing, producing, and deploying superior defensive technology possess overwhelming advantage over those relying on courage alone. The contrast between proximity fuses and kamikaze attacks tells the larger story of industrial warfare in the 20th century. Victory belonged to those who could marshal scientific knowledge, manufacturing strength, and organizational skill to create better weapons. The proximity fuse was the culmination of American strengths, innovative engineering, mass production, and disciplined execution. Its triumph over the kamikaze established technological superiority as the foundation of post-war military doctrine. It did not merely defeat a tactic, it proved definitively that in matters of life and death, quality of equipment could overcome quantity of sacrifice.